off, so you just get on the toe next to it. So.
Oh.
Sorry to hear that. That's what being in season's like, just a constant state of soreness and pain.
Kyle's definition of pain.
It's the Gaelic word for pain, isn't it?
Yes, today.
Yeah. So I was thinking here, to pick up a new rhythm with the homework, and just let me know what you think of this. Smaller assignments, just have one a week, just smaller, so they're not like, cause like in the past I'm like, oh, I try to do a bunch of problems encompassing a bunch of different things, and then they end up like taking like too long. So smaller assignments, does this sound good? We can try it, and you know, like if you're running late, just let me know. It's no big deal. We're a small group. We work together. For example, I don't have your first ones graded, but I will definitely have everything graded by next Monday. I was traveling over the weekend and just couldn't get it. So here's the next homework assignment. I guess this, bless you. Would this be homework 3?
Yes.
Yeah. So this is chapter 3. Problems 1, 4, 8, 9, 10. We might even have time today to start on it, which would be kind of cool. So again, please, questions on Monday, right? So this is going to be due next Wednesday. Let's at least shoot for that, and then let's have questions on Monday. And what these homeworks will hopefully do is be like really focused on whatever we covered for that particular day. Or, yeah. Awesome. Outstanding. Does anybody have a homework for me today? Anybody need more time on that? Okay, great. Thank you. Thank you. Lovely, lovely, lovely. Wunderbar. All right. So, let's, I got some questions for you. Just take a minute. No notes, and I'm not going to collect this, so, you know, there's no karmic debt to be paid. Take a minute, think about it. Do you know the definition of that, Mike? Could you state a nice, clean definition? Anybody think they got one for us? Sydney?
It's like all the integers below n that are relatively prime to n.
Yeah, it's beautiful. Absolutely. So integers between 1 and n. We could say positive integers, just to be clean there, because otherwise we have a big infinite collection, right? But I knew you meant that anyway. So yeah, u sub n, or u of n, is equal to the collection of all k in Z plus, such that k is relative, such that the GCD of k and n equals 1. And that's just relatively prime. It just means there's no factors other than 1 that they have in common. Yeah, and n wouldn't be included in that, because if we put n here, then the GCD of that would be n. So this is a nice way to get it out there. Let's see, I had another question for you based on that. Why? Why is u, now here's the deeper question. Why is u sub n defined this way? We kind of talked about this last week. I just want to see if that was actually, I'm going to check my recording and make sure it's kosher and rolling, and it is. Why is that? And anybody can pipe up anytime on that. Why, and let me help. Let me refresh your memory. So let's say, this isn't the correct definition, but what if I had U4 and I just went ahead and included some things that weren't relatively prime to 4? Like I put that 2 in there, right? So why is that a problem? is the assumed operation on UN? We know it's a group. Yeah, it's a group. Under what operation? Oh, I'm glad we're having this talk. This is a good talk. If I make a table for this is, I'm gonna, not really, just in case anybody looking at this video thinks I think that's U4. Not. 2, 3. What's the op?
Multiplication.
It is. It's yeah, multiplication mod n. Yeah. So this is mult mod n. This would be mult mod 4 here. So what's this table? Yeah, let's do the easy part. We have an identity, right? 1, that's nice, and k clag. What's 2 times 2 in mod 4? Ooh. It's like, no bueno. Not bad, no bueno. It was just casting sounds about. So, why is that no bueno? Because what? Yeah, true. Why is it not a group? Not close. This is an element outside the set. So right there, that's bad news. Let's do 2 times 3. What's 2 times 3 in 2? Well, let's finish this table up. 6 goes 2. Yeah. And then 9. Cool. So that's not closed. What's another problem? What else do we need for groups? Let's go identity. Identity. So we do have an identity, right? So yeah. What's wrong with this? What's missing here? I think you're.
Yeah, there's no identity.
There's no identity. So we wish there was a 1 there. Why? Inverses. Because of inverses. Perfect. So the fact that if I include factors in here or numbers in here that aren't relatively prime to the n that's the base, I'm going to end up getting non-invertible elements. So I want everybody to have an inverse, and I also want this thing to be closed under multiplication. So why? To ensure it is closed under mult mod n, and that every element has an inverse. Cool. Would you get your books out, please? I want to check out, I think it's page 47. Or share. Share.
I got mine today.
Yeah, I know. I'm proud of you. You don't have your toes, but you got your book. That's something.
I don't have all of the retail.
You got all the book.
Yeah.
Yeah. Diana, do you have access to a PDF or anything? Okay, awesome. So yeah, on page 47, I kind of wanted to talk about these group examples because we haven't spent a lot of time talking about many groups, except we've spent more time on UN, I think, than anything. But let's take a look at these classic examples, and these are things that you're going to want to have at your disposal because they help you understand groups, and they also might be counterexamples of things or just examples of things. So let's go through here. So actually, let me get up on the board and write out a few of these. So the first one is lovely. We have Z under addition, just classic addition. So as soon as you get the set and the op, you should be able to come up with the various identities and things like that. You can probably read it off the table, but can you tell me what the identity is here without looking at the table, or just because you do understand? 0, right? Because a plus 0 is equal to 0 plus a is equal to a for all integers. Yeah. So if I have an element a, what is a inverse? We use this notation, but what does it look like in this group? Negative. Yeah, so it's actually the opposite of A. So this notation here is kind of a multiplicative notation. We associate it with multiplying things, you know, add the exponents and all that. But in an additive group, the inverse can easily just be written like this, just a negative. Cool. And then abelian. So remember, what does abelian mean? It's a good day. Good day. That's okay. You're gonna be real soon. What's an abelian group? Well, I can look it up. We can look it up. It means it's commutative. So abelian just means all elements commute. It's just a fancy way to say that. We like to set all sorts of gates to keep people out of our mathematical community, so fancy words are one of those, you know? Like, oh, no, abelian, oh, la-ti-da. Well, no, I just, this. Okay. So this is abelian. Yeah, addition is commutative. So we have a nice abelian group. Check out the next one, Q plus. So we have Q plus. Under multiplication. So we have Q plus and then standard, I'll put a little dot there for standard multiplication. What's the identity? Identity is 1, so equals 1. What are the inverses? So if I give you some Q, let's call this G. If I take a Q, that is a weird looking Q. Everything's starting to look weird now because I'm writing weird. What is Q inverse? So let's take something out of here. Here's 3/4, right? That's in there. Yeah, what's the inverse of that? 4/3. And so it literally is, and Sydney, you had said this last time, and I said, we don't want to write that, but here it does make sense. Because it literally is a reciprocal. In general, like think about if Q was a matrix. That was what I was trying to like keep us from doing. So you wouldn't write 1 over, you know, some matrix down here, right? Because that would be pretty weird. We'd at least have to define that well. So, nice. Is that abelian? Multiply a couple fractions in any order. Right, all the things you know, don't worry. Everything you've ever learned about numbers still holds. It's okay, or this is just basic arithmetic and you got that under control. It's super fancified. What about, okay, so we did inverses, we're good there. And then this is a really important one, the next one, Zn. So the integers mod n under addition, where's me eraser. Slipping into this weird, like, pseudo-Irish thing. I ran into Dr. Bowie and Palmer this morning. Top of the morning to you. And Palmer knows, man. He was just like, may the hill rise to meet you, my friend. I can do that. I'm not like, we're like partly Cornish. Trenner, he's Cornish, so not like appropriating or mocking or anything. So we have Zn, and that's the integers mod n. What's in this group? Where's it start? And under addition, so we got good old plus mod n. Plus, like what's the identity going to be for addition? 0, just like it always is, right? So this is just normal addition. We just like keep cycling, so that's okay. So we definitely have 0 in there. How far up does this go? N minus 1, beautiful. Because if I put in n, what's that equivalent to? If I did this, what am I being redundant about? The 0, right? That's just 0. It's equivalent to 0 mod n. So all multiples of n. So we don't want to go up that far. We want everything to be nice and unique. Here's a tricky one. If I give you a k in z mod n, what is k inverse going to be? Let's go ahead. Yeah, the complement, n minus k, because, so this is going to equal n minus k. Nice, Kyle. Because this is really, well, let's talk about that. So k inverse is this. So if I took k inverse, there, and I wrote it like this. This is this is actually addition. Right? I'm just using fancy notation. And so this is k plus n minus k. And that just gives me n, and that just gives me 0. So good job. Yeah, it's just that complementary bit that gets you all the way to full revolution. Good stuff. Is this abelian? Sure is. Because it's just addition again. And then modding. And modding doesn't change essential properties like that. So we're all good to go. Here's one the next couple. These are kind of the same, kind of not. We've got R star, which is I think what they want here is the reals sans 0. So I think this is just R minus 0. I don't think it's only just the positives. Yeah, let's see. Let's actually check that out. Does anybody see the definition of that anywhere? Just so it's probably in the previous pages. I think it's just non-zero. Yeah, because C star. So then the complement is the complex numbers minus 0 as well. That's C star. And these are groups under multiplication, standard multiplication. And so inverses are just going to be 1/overs, reciprocals, just like before. That whatever that dude was down there. All right, let's take a look next. Oh, so this is one that we don't, certainly haven't talked about a whole lot. So let me write this up here and explain what it is. We kind of looked at something like this. This stands for general linear group. So this is the general linear group. These are matrices. And this first, the n by n matrices, this first number here gives you the n, so it's kind of the dimension of the matrices. There's just 2 by 2s. This F stands for a field. And that's a mathy word. It's a much fancier algebraic structure than groups. It's something you're used to working with. Like, for example, classic fields are going to be R or C or UN is actually a field. Methinks, you better check. Why am I talking like that? Sometimes you ever do stuff and you don't know why. It happens to me all the time. Let's see, so, actually not, I think this UN would work, but they are giving Z mod P, where P is a prime. So that's under addition. And then what else could it be? Sorry, I lost what I was just looking at here. Yeah, or Q. So it's just a place where you can multiply and add and divide and do all sorts of good things. All the kinds of things you just want to do with numbers. All right, so that's that one. Just know that that is matrices. Oh, and with an important part, we need to have inverses. So we have to have the determinant non-zero. Which I think we saw an example like that on, when was it? Monday? Yeah. Do you remember when I was trying to find a non-invertible element and I knew that the determinants had to be 0 if it was non-invertible? Does any of this ring bells? Yeah. So that's where I was thinking about. And then the rest of this,
Oh, here's kind of our last one. Ooh, is this abelian?
Is matrix multiplication commutative?
No.
Not at all, right? In general, not. So this is definitely a nice example of non-abelian. Everything else has been abelian so far. All this stuff is just kind of classic and abelian. Here's one more group that is non-abelian. So D sub n, this is the dihedral group of order n, order 2n actually. But the way to think about this is it's the symmetries of an n-gon. So remember how we looked at the triangle very first day, and we had this triangle, and then we had 3 rotations, and we had 3 flips over various axes. So this was a 3-sided figure, and we had 6 different elements in the group. 1 for each rotation, 1 for each flip. So this is just the symmetries of a regular n-gon. And regular just means all the sides are the same length, all the angles are the same. What are the operations here? So over here, all the operations, that was addition, this is multiplication. Here it's matrix multiplication times addition. What is the operation here?
It's a composite. What he said, yeah.
What did you say?
Composition.
Yeah, and you said it too. It was like simultaneous. It was just like opposite ends of the world, people thinking the same idea. Yeah, absolutely. So this is the operation equals composition. What is the identity? What was the identity here?
R sub 0.
R sub 0, no rotation at all. Yeah, beautiful. So E was R naught. And if we compose that, if we don't do anything and we compose that with something, we get the other something, right? It's like, don't do anything, then do this thing. You get that thing. Inverses are a little trickier, for sure. We'd have to, that's too fancy to work out. Was this abelian? It was not abelian. Remember that table was not symmetric. So a symmetric table down the diagonal is the hallmark of an abelian group. So this was non-abelian, just like the one above. Okay, cool. Little bit of group review. Let's see what time we got. Good. I do want to give you just a little to at least look at the next homework. Let's talk about a few basic group properties and then one definition. This won't take long, but I want to make sure we address these things. They're just natural consequences of the definition of a group. So I ask you really quick while I'm erasing, define group on your paper. What is the definition? Like imagine it's a quiz. It's not. Imagine it is. Define a group. Once the pink pen is out, you know it's done. Is that true?
Yeah.
vortex.
Purple one's kinda nice too.
What is?
The purple one's kinda nice.
Yeah,
too.
purple's sweet. Wait, where's the purple in there?
I use it for my
Like,
definition.
boy, it looks really pink. That's purple?
This is purple.
Oh, wait, the writing, not that pink line. Okay, okay.
Easily confused.
Easily confused, yes. Okay, gotcha, yes. Sydney, you seem like a person
Oh,
who has a definition in pink.
incorrect. I have all the properties of a group though.
Okay,
Best
alright.
I can do.
So what do we need to have a group? Tell me just like the basic, what's in the stew?
I love the way you talk.
Some beef, potatoes.
Carrots if you're vegan.
Go,
Yeah.
okay.
I'm not much of a carrots person though.
I'm a vegan, so I'm not eating your stew.
I mean, you gotta have like
A what?
a what?
Yeah, yeah.
Like a set of things.
So is a set, beautiful, S, cool,
Cool.
Progress.
progress, exactly.
Got the beef in the stew.
This is stone soup here.
And then you have like the properties that those or that those elements have to satisfy. That's where I can get you.
Cool, yeah, and you're right, that's 100% right, but what is the link, before we can talk about properties, what do those properties reflect? There's something else, we have a set, S, is, if I just give you a set here, you know, or, weird, but, is,
5-4.
yeah, is that a group?
Operational.
You need an you don't know what the
Jump out.
operation, so we need an op.
Cool.
So that's the other thing, so we need a binary operation.
You need the broth.
Exactly, exactly.
I love this class.
A binary operation. And that might be multiplication, it might be composition, we don't know, it could be some weird thing we have never encountered before, a binary operation. So, and then, Sydney, yeah, then some other properties that relate these two things together. What are those properties? With the properties, what?
You need some associativity.
Associativity, I'll put that at the bottom because that's like our hand wavy.
You need an identity.
Beauty.
An inverse could be cool.
And an inverse for everybody, right? Inverses for all. Cool. Yeah?
Cool.
That's a group. We'll play this game very often, where we come in and just try to remember, where am I? What am I doing? Always good to check. These basic questions sometimes are the hardest.
Yes.
Sometimes the deepest too. Cool, so we've got this group, and here are some nice little consequences and facts to know. Consequences and fun facts. So first off, the identity is unique. I'll write it out like this. The identity is unique. And to prove this, to prove something's unique, a classic technique is to assume it's not and show that that can't be the case. So assume we have, and there's also some little techniques in this that you're gonna see that you'll have to get used to, so this will be a fun talk. Assume we have two identities. IDs. And they are E and E prime. So, for all A in G, for everything in G, we have A is equal to AE is equal to EA. Notice that the identity commutes with everything. That you always get. You always have commutivity of at least one element. And also, I know that A is equal to AE prime is equal to E prime A. So now watch this. I'm gonna let A, I'm just gonna replace A with E prime in this top statement. So thus, E prime must equal E prime E. Right, because E is an identity.
But E prime is also an identity, so E prime times E has to be E. So they must be equal. It's so subtle, right? It's so subtle that you might not even know how to do it. It's just gentle and profound at the same time. So there.
There.
Boom.
Boom, exactly, in your face. Okay, then, so that's one of the properties. The identity is always unique. We also have a thing called cancellation rules. So we have left and right cancellation are possible. So notice how I'm not just saying cancellation. We have to be super careful in a group. It might not be abelian. A couple of our really big groups are not abelian. So what I mean by this is that if I have AB equals AC in a group, I can multiply both sides by A inverse or cancel the A out. That implies B equals C. And also, if I have BA equals CA, notice here that the thing that I want to cancel is on the same side in both these, and that's super important. That implies B equals C as well. The proof here for this one, so I'll just do a little proof. It's more of a proof than a proof because I'm not going to say a lot about it, but I'm going to left multiply each side by A inverse. So let me show you how this works and the kind of detail and precision I want you to do these operations with. So let's take this thing. So originally I had AB equals AC. I'm going to leave a little room to the left here, but I'm grouping those together because that's the way they came, and I'm going to left multiply by A inverse, which makes sense. How do I get, what property allows me to regroup this so that the A inverse and A primes are together, or excuse me, the A inverses and A's? Associativity, right? So associativity allows me to move the parentheses. So by associativity, this is A inverse A, B equals A inverse A, C. And because of those are inverses, I have EB equals EC, and the identity, which we know how that works, implies B equals C. Same, can you imagine how this one goes? Just right multiply by A inverse, and you knock that out. Cool, but be really careful. So in general, unless you know that the group is abelian, unless we know G is abelian. If I had AB equals CA, I can't do anything with that. There's no cancellation possible. Is non-cancelable.
Interesting.
What's that? Yeah.
Interesting.
Yeah, indeed. But if I do have abelian, then I can change the order and knock them out. All right, we got one more. Inverses are unique. There's only one inverse for everybody. So let's assume that A is an element of G and G is a group, and G is always going to be a freaking group. If you see a G on the board, just assume it's a group. If I didn't say so. Assume A is an element of G, and then let's assume it has two different inverses, and AB equals BA equals E. So in other words, what I'm saying here is B is an inverse, i.e. B equals A inverse. So another thing that commutes is the inverse. The inverse works on either side. You always can commute with your inverse. But also, I have
AC equals CA equals E. And what I'm saying here is that C is also an inverse of A. Can you help me come up with a proof to prove that C has to equal B? Besides that setting those two things equal. Let's actually get rid of those. I just wanted to point that out. I'll write this out. So B is the inverse and inverse of A, and here I'm saying C is an inverse of A. So I'm trying to do this in a flow where we can use things that we've just done. Can you kind of see, Trinity, how we might, yeah, please, regale us.
If you just do, because AB is equal to E and AC is also equal to E, so these are equal to each other.
Beautiful, yeah. And that's also equal to, like, is this what you were saying? Yeah. So because this is E and that's E, AB must be AC. So AB equals AC, and then what is the property that allows me to say B equals C? Yep, beautiful. Thus, by cancellation, left cancellation, how about we be really clear? B is equal to C. Cool, that's an easy proof, right? But these little techniques, your proofs are gonna feel a lot like this. And then we've got last little thing, this is kind of a definition, and it leads into just really the only new idea I want to talk about today, which is one obviously you've already seen it, so it's nothing stunning, no stunning revolutions or revelations or anything like that. Okay, so powers of an element. So if I take A as an element of G, then A inverse, we know that's, when I write -1, that is for us the inverse of A. We've been using that lots. We're pretty used to that by this time this semester. But if I write A squared, well, actually, let's slow down. A to the 0, we're just going to define to be, what do you think? It would be 1 if we were in a multiplicative group. Yeah. So for us, it's going to be the identity. Because we don't have a 1 necessarily. We might not have numbers at all in this group. A to the first, just good old A. A squared is just A times A. You can't go wrong on that. There's, commute all you want, not mixing anything. And in general, A to the n is just n copies of A multiplied together. Similarly, I can do negative exponents. So for example, A to the -2 would be A inverse squared. Does that make sense? So that's going to be A inverse, and on down the chain, So in the end, what we've got is this endless chain of powers. We've got A to the 0 is E, and then we've got A to the first, A squared, A cubed, and then down this way, we've got A inverse, A -2, A -3, and that goes on forever. I can keep doing that as much as I want. I might not get new things eventually. They might wrap around. I mean, if you only have a finite number of elements in your group, you shouldn't expect these to all be different, right? Something's going to have to repeat. Do you know the pigeonhole principle? You ever heard of this? This is a great mathematical principle. If I have a bunch of pigeonholes, so here I've got n pigeonholes, and they're just pigeon houses, right? Pigeon homes. And I have n plus 1 pigeons. One of these must have more than 1 pigeon in them. And it makes so much sense, right? That makes sense. But my God, this is one of the most powerful ideas in mathematics.
if you, in combinatorics, I don't even know, did we do this in combinatorics? Was anybody in combinatorics with me? No? Okay. I gave a little 30-second lecture on this one time here at Regis, a long time ago, when we did things like that. Doesn't seem like we do anymore. But, so if I have a group of order n, and I only have n boxes, and I've got infinitely many pigeons, I imagine lots of these boxes are gonna have multiple pigeons in them. And that's all I'm saying. Some of these things have to be the same eventually. Boy, that pigeonhole principle is powerful. For example, there are in this town, let's say Denver. In Denver right now, there are at least 2 people who have exactly the same number of hairs on their head. Exactly. And I know that for a fact. And I know that for a fact because the average human has, let's say, roughly 100,000 hairs on their head. Some have none, some have more, but roughly 100,000 hairs. So let's take all the boxes here, and the boxes are going to be number of hairs on your head. So this is equal to 0, 1. So bald folks go here. You know, like Howard Stern goes way out here. He's got a freaking shitload of hair, right? So just think of someone with lots of hair. They're going to go out here. But each one of us would fit into a box. So there's only around 100,000, let's say that at most 200,000 hairs on the head. I don't think anybody has more than that. How many people live in Denver? A lot, like more like 700,000 people, at least a couple of years ago. There's 700,000 pigeons that have to go into 200,000 pigeonholes. One of these will have at least 2 people in them. So I know for a fact that there are 2 people in Denver with exactly the same number of hairs in their head. I don't know how, I don't know which box they go into, but they will be in there. That's pretty powerful, right? That is, it's just kind of a stunning claim that is actually completely true. And obvious thanks to pigeonholes. Okay, so I've got all these powers of A. This is the cyclic subgroup generated, and this word is going to become very important to us starting on Monday, generated by A. And we denote it like this with brackets, A. And it's literally just all the powers of A, all the integral powers of A. And nice things work here, you know, so any element in here is going to have the form, it's either going to be A to the M, I take it times A to the N. And by the way I've defined this, those laws of exponents just work. Here's m a's multiplied together, and here's n of them. So there are in total m plus n of them. So those nice laws of exponents work. I've got an identity. So this thing is a group itself. This is a group within whatever group A was in. So you take A from the group, you look at all its powers, and it generates a group on its own. You can forget about everything else and focus only on this. This is a group. What's the inverse? So if I have A to the M inverse, that's just, what do you think? A to the negative M. Exactly. Yep. Because A to the M times A to the negative M is just going to be A to the 0. And we've defined that to be E. That is E. We've got associativity because just laws of exponents, we got all that. We've got inverses, so this thing is a little group unto itself. The one thing I have to be careful about is when I start combining elements from G and looking at powers. So let's just take a look really quick at a subtlety here.
So be careful of powers of products. And again, products doesn't mean times. It just means I've got these group elements interacting together. So for example, if I had AB squared, that's not A squared B squared. You wish, but it ain't. This is AB times AB, and the best I could say is it's this. What do I need for this to equal A squared B squared? What do I need to be able to rearrange this? Because I can't unless I know something. A billion. Yes, exactly. It's yeah, it's all good. Yeah, you saw the word. I think you said like ablein, and I like that or something. I like it. It's enabling commutivity. So it's only equal to A squared B squared if and only if the group is abelian. Notice abelian is capitalized because it's Abel was a mathematician. So be really careful with that. Just let's see. Was there anything else I wanted to say about that? No, but I do have one last thing to say about this thing right here. So, what was it? I already forgot it. Last definition. So the definition: the order of an element A in G is so that's what I'm defining. The order of an element is the smallest integer n such that, and let's do plus positive powers, such that A to the n is the identity. Let's look at a couple examples. So for example, let's take a look at good old U21. Can you write out U21 for me, please? Oh shit, let's start out let's start to reverse, no, it's okay, but yeah, sorry, we'll get to that. Let's flip those digits and have something a little more manageable first. Let's start with U12. Write out U12, please. U21's huge. What's the table look like? Make a Cayley table. Doing this stuff, doing lots of these kinds of computations will really make you stronger in this class. So that's why I'm doing it, not just so I can think about other things for a brief moment. Remember that one little trick about Cayley tables? Each element appears exactly once in each row and column, so the Sudoku thing. It's pretty. Really pretty, right? But then sweet, and you can just enjoy the fruits of unique elements, and I have each row and column. Yes, thank you. What is the order of each element in this group? What's the order of 5? So the order of 5, and we denote that with kind of these absolute values, almost like magnitude. What power do I have to raise 5 to get the identity? 2. What's the order of 7? 2. And the order of 11? 2. Awesome. What's the order of the whole group? What does that mean when I say the whole group? 4. Yeah, it's a number of things in it. The order of this group is 4. Just want you to notice that each of these divides the order of the group. That will end up being like one of the most absolutely critical observations that we're going to make in this class. Let's take a look. Now let's go to U21. U21, please knock that out. I'm not going to ask you to make the whole table because that will eat up a lot of time, but I will ask you what's the order of U21, and then I will ask you what what's the order of 4 in this group? I'll be right back. I'm running the restroom. Yeah, that'll certainly take some time. So you're cranking out powers of 4. That would be the way to do this. You already got it?
I think so.
Nice, cool. So just a little note that what you are doing to answer this question is cranking out all the powers of 4, the cyclic subgroup generated by 4. Let's get all the elements together here first. So there's a lot of shit in here. Not 6, not 7, 8, 2. Aren't you glad we're not making the Cayley table? Even though that's like a really soothing thing to do for a mathematician. 16, yeah. 17, not 18, 19, 20. Does that look like what you got, Kyle? Yeah. So what was the order of that? How many things are in there? 12, thank you. It's group order 12. Now we have to crank out these powers of 4. We got 4 to the 0, 4 to the first, 4 squared. And we have to figure out where does that end? And 4 to the 0, that's easy. It's just 1. 4 to the first is easy. And then And they're easy until I end up having to wrap around. So 4 squared is 16. That's in the group, that's cool. 4 cubed, now things get a little weird. Doing these mods, remember I showed you this little trick last time? I like to write down the multiples of the n. So it's easier to just subtract off a multiple of the n. So we've got 42, 63, 84. Might as well keep going because I think these numbers get pretty big. So that's 105, that's 126, and then 147. I think I need one more, maybe not, but I'll just do it at 168. Cool, so 4 cubed is 64. Is that right? Yeah. And so what's 4 cubed in this group? 1. And I'm back around. I just wrapped around. So the only thing in this group are these 3 elements. What is the order of the cyclic subgroup? Indeed. Note that that divides the order of the upper group. Yeah. I clearly did this wrong on my own. I did like some work and I was like looking at what I've got here. Oh, no, that's something else. Let's do the, yeah, okay, one more. What's the order of 10? What is the order of 10? Yeah. So cyclic subgroup generated by 10. I'll give you a first couple, there you go. What an asshole, sorry. It's just powers of 10, right? It's not too bad. Let me give you a tip. Let me help out here because you're probably like 1,000 mod 21. What the hell's that? Let me show you some neat tricks here. So, so it's good. So the next one would be 10 times 10. So 10 squared is 100. I can still do that pretty easily, right? That's just 16.
Yeah.
So I know that all of these things are equivalent to powers of 10, right? So this was 10 to the first, this was 10 squared. If I multiply this by 10 again, actually that one's not too bad either, right? So here's what in other words, here's what I recommend. When I take 10 cubed and I want to do that mod 21, notice that that's just 10 squared mod 21 times 10 mod 21. So I can take the modular version of 10 squared times 10.
Okay.
Instead of going up to 1,000,
Yeah.
right? So this is 10 squared here. So 10 cubed in this group is going to be 16 times 10, that's 160. That's a lot easier to deal with to get 13, yeah?
Okay.
So that's 10 cubed. So can you see what's 10 to the 4th now faster? It's 13 times 10. 13 times 10 is 130, which is 4. There's 10 to the 4th.
Interesting.
Isn't that cool? And it's so much faster.
Yeah, it's better than.
It is, it's a lot better. So what about a 10 to the 5th? Yep, so it's 10 times 4, 40. 40 mod 21 is 19.
No, just kidding. You're so right.
That's a good one. 19, does that make sense, Sydney?
Yeah.
Yeah. And then what about, so that's 10 to the
There
3rd.
it is.
Did we wrap around?
Yeah.
So yeah, the next one is 10 to the 6th, which is 190,
And then 168, 189.
which gives us 20, so 190 mod 21.
Yeah, you got it. 168 plus 21 is 189. That's 22.
That's 22.
Right. And then
Oh, okay, and then that's, yes, cool, got it, yeah, that's back in the group. Yeah, cool, got it. Probably if I'd gone up one more multiple, that would have been
yeah.
that would have been the thing to do here, right? So yeah, 189, geez, right there. Yeah. So it's 1 again. And so we're done. So this is the cyclic subgroup generated by 10. Sydney, you're making furrowed brows, is
I
that
was
cool?
Just adjusting my eyes.
Okay, gotcha. What's the order of 10? 6. Divides the order of our group. Yeah. So there's some tricks on like how to do this stuff a little easier, less painful ways to do a lot of this modular.